Hello friends, welcome back to my YouTube channel. So today this is a presentation which is introducing for you the system that is developed about the graph reasoning large language models for inclusive home-based mathematics education in Uganda. So basically, this is a model, a system that is trained to enhance the way education, primary mathematics is delivered to the students, especially regarding the children with intellectual disabilities. Yeah. So, of course, before starting to this work, we had some literature, some related work that was established before, that was published before, that we went through just to get a broader view of what we are going to do. And among this work was the Attention is All You Need. Attention is All You Need was a paper. Well, it was published in 2017, and in this paper, transformer mode was introduced. Yeah, so among other papers that were published before in the same line as ours. So we went through this just to get a brief understanding of the model we are yet to develop. And of course, each model we are indicating here the results from the model, the architectural limitations, and the content limitations. Yeah, of course, this was just a brief to go through to get a brief understanding, and we won't waste a lot of time explaining this. So the problem, as listed earlier, our domain problem is about education. Education, how mathematics can efficiently be delivered to the students, especially those with intellectual disabilities, and want it to be a home-based. Yeah, how can the caretakers or the caregivers, how can the parents at home academically support their children at home when they have left the school, they come back home? How can these caregivers academically support them so that they can enhance their ability to do mathematics? Yeah, and among the questions that we had to ask to give us a broader view of the project are, how can home-based caregivers support mathematics learning efficiently? Of course, especially attending to students with intellectual disabilities. Then, how best can we make this system less costly, less expensive, so that it can be accessed by the majority of the people, so that they all can benefit from it? And among the objectives of the system of the project was to develop an AI-powered co-teaching tool. Yeah, and as we successfully develop it, yeah, and this tool had to be able of generating information related to the mathematics teaching, such as the lesson plans, such as the course outline, the teaching strategies, as well as the evaluation exercises to evaluate whether the learner has effectively got something or not. Yeah, and the outcome, of course, we successfully developed this model, and it is now running safely on the servers of the Hugging Face. So the system, the methodology and the system architecture, of course, we use the graph-based retrieval adversarial fine tuning. And of course, here, this uses a graph, knowledge graphs, in order to, the knowledge base is represented by graphs with nodes and edges, such that the model can know the relationships between the different nodes. So it all starts with data collection, where we collect the data, and for our case it was a customized data, because we didn't have ready data sets that we can just get. So we had to customize our data by fetching different documents from the NCDC, different PDFs concerning the different teaching methodologies, different intellectual disabilities. Yeah, and after getting that, we construct a knowledge graph, and basically we used NEO4 Neo4j, to come up with the knowledge graphs. After getting the knowledge graph, of course, we trained the encoder, and for our case it was the RGCN, the encoder. And after this encoder is trained, you will get the embeddings, and it is this embedding that we feed into the model in order to fine tune it. And of course, for our case, the model is the Falcon, the Gamma, and the Llama 2 that we fine-tuned. And after that deployment, of course, among the three, we chose the best model, and it is what was deployed. And after deployment, so it is the reviews from the users is what we are waiting for, such that we can enhance the model's output, the model's functionality. And this is the architecture of the model we used. Of course, all the models we trained, we fine-tuned a transformer-based architecture. For the transformer, it has both the encoder and the decoder. But for this, the Llama, the Falcon, and the Gamma 2 are only encoder-based architectures, encoder-based models. So they only have the encoder. And the flow of information is concerning this architecture. It starts with the input as in the user input. After that, after getting that input, the data we are using to train the model, then that data is tokenized into simple tokens. A sentence is broken down into simple tokens, and then those tokens are converted into embeddings, vectors representing each of the tokens as it is in the vocabulary of the model. Then after that, we furthermore go on to find the positional embedding. The positional embeddings are there to indicate, to guide the model, to tell the model what the position of which term, of which token in the sentence. Then after that, it either goes to the normalization layer or it goes to the multi-head attention layer. So in the Llama 2, it is the normalization below. In the rest, in the Gamma and the Falcon, it is the multi-head attention layer component before, then the normalization layer after. So this under the multi-head attention, this is where attention occurs. And attention specifically, we want each token to attend to its neighbor such that it extracts the information and it gets the total, the model gets the total structure. So each token attends to the nearby tokens using the its queries to examine the keys and the values of the other of the neighboring tokens so that it can collect the information and the model gets the structure so that each token is adjusted, the embedding of each token is adjusted to include the structure, the context of the system of this sentence, of this text it is examining right now. Then after that, the normalization, some of them use the layer normalization, others use the root mean square normalization. Then after normalizing, data is fed into the feed forward neural network. After that, again, it is normalized. Then after normalizing, we have the linear component. This linear component is just to match the embedding into logits, into output logits, and these logits are as in they are mapped to the tokens, to the embedded, to the vocabulary to the vocabulary of the model. After that, softmax happens such that the probabilities, these tokens, these embeddings are converted into probabilities. Remember, transformer works on a basic of predicting the next token. So the output should be probability attached to each of the terms such that the term with the most, the best or the higher probability, the one is the output of the system, of the model. So the math below, we have the soft attention, as we said earlier, which uses the query, the key, and the value embeddings. And here we take the query and the transpose of the key over the dimensional matrix of a given system, be it Llama. For the transform, I think it is 512, so it will be root of 512. Then after that, we get the softmax of that. Then after we multiply by the value embedding. Yeah, so that the attention, and remember we said for this one they use a multi-head attention. So we have various heads, each head attending to different version of the sentence, and after that all of the heads are concatenated together such that the entire meaning of the sentence of the statement is captured properly by the model. Yeah, so here we have the normalization. As we said earlier, some use layer normalization, but for our case, we had the lemma, which uses the root mean square and normalization. After that, we had the feed-forward neural network, and of course, it is all to enhance the understanding of the model, each term in a given sentence. So it uses this feed-forward neural network to understand each model using the activation weights to understand each model deeply, each token deeply in the given sentence. Yeah, so these are the functions. These are functions for the feed-forward neural network. The formulas, we have the SWIGLU, we have the ReLU, but specifically for ours it was using the SWIGLU. So briefly, this is the data set. As I said earlier, the data set was customized because we had no ready data sets to use. So we had to capture the data set using the National Curriculum Development, the National Council of Curriculum Development, where we got the topics, the classes, what the content to be covered, then using other necessary PDFs to indicate the teaching methods, to indicate the disability types, of course, intellectual disabilities, as well as the physical disabilities, some of them. So after that, the data was cleaned properly such that we had no missing values, and the NEDA, of course, was carried out. So basically, we got 13 columns and at around 715 rows. Yeah, so that was the data the data set that we use, a customized one. So we had no missing values, and if we observe the EDA, so this was an EDA just to help us examine the data set, indicating the common teaching strategies here across the different disabilities. So we can see that the common teaching strategy so this is only indicating the common teaching strategies. We have the inquiry based, we have the discussion based, depending on the disability and the topic that is being taught. So this is just a simple output of the model. As I said earlier, the data was properly cleaned to remove duplicates and missing values. So we didn't have any missing value, so that you can observe from the heat map here, all of the classes, subtopics, what had no missing value at all. So furthermore, further understanding of the data set. So these are just a disability, the distribution. You can see that P3 was having the highest number of the disabilities. So P3 class, all of the disabilities are represented here. Yeah, so here we have the distribution of the disability type. You can see that our data set was somehow biased, so that it had a lot of rows in having the people with no disabilities, and you can see that the intellectual disability, the multiple disability people with multiple disabilities, of course, they were not represented as much as the rest. So I think that will cause might affect the functionality of the model, but okay, nevertheless, furthermore, further understanding of the model EDA. Then this was the output. So we trained 3 models, the Gamma 2, the Falcon 3, and the Llama 2. And of course, as you can see, it was the Falcon 3 with the best results. So we had a loss of 1.2, a perplexity of 3.39, have the ROSE 1, the ROSE L, the BLEU, and specifically it was Falcon 3 which produced the best outcome compared to the other, and that's why we chose it, and it is what we deployed. Yeah, so this is the explainable AI results. So you can see this is for the Falcon 3, this is for the Gamer, but somehow they are related. So you can observe from here that this part here, right to the diagonal, it is completely dark. Why? Because of the masking effect. We don't want the model to use to be able to see the future tokens, because we want it to predict basing on the previous tokens. That is why all of this is turned into zeros when carrying out the softmax such that the model does not see it. So this is the expandable AI. Of course, we can see that the model gives greater attention to the last tokens, as you can see here. And of course, each token and yeah, it is just a heat map. Here we have a token and how the other tokens attend to that. Basically, that is it. From here, we can see which tokens influence the output of the model. So from here, the red indicates that that token is given much attention compared to the rest. It is red, then blue. So the red greater attention, then blue it is less attention. So we can see that in such an equation, it is which is given the more attention than followed by these tokens, the mathematics, the students, and so on. So basically that is it. And here we have the limitations of each of these models, of course, such as the computation space, the GPU that they do consume, and among others. So under the deployment part, as I mentioned earlier, we deployed the Falcon 3 because it had the best output compared to the rest, and it is now running on the Hugging servers here under our space, the Edu Vision, and we use the Gradio for that, of course. So as you can see, this is a simple interaction with the model, where a simple prompt was given to the model for testing. So I told it to give me the outline of the topics in primary 3, and this was the output, as you can see here. So basically, that is it, friends. Thank you.